Hello and welcome to the last section of Chapter 5. Today we're going to look at 5.5, which deals with multiple angle and product to sum formulas. While in this section, we're going to look at 4 other categories of trig functions. Those 4 other categories are going to deal with multiple angles, and that would be something like sine of some constant k times u, so it would be like the sine of 2x or the sine of 5y, or however you want to phrase it. We're going to look at squares of trig functions, something like sine squared of u. We'll look at half angles, and this is where you have the sine of u divided by 2. Or we're going to look at products of trig functions, so sine u times cosine v, etc. And in order to look at those 4 types of trig identities, we're going to start out by looking at what we call the double angle formulas. Now, what you're going to notice in this section is there are going to be a fair amount of formulas that are given to you. I will give you a sheet that you can use on the test and any quizzes that pertain to just these formulas in section 5.4 and 5.5. Everything else you do have to know. So, when we look at our double angle formulas here, if I have the sine of 2u, then I can rewrite that as 2 times the sine of u cosine of u. If I have the tangent of 2u, I can rewrite that as 2 times the tangent of u divided by 1 minus tan squared of u. And if I have cosine of 2u, I can rewrite that as cosine squared u minus sine squared u, or 2 cosine squared u minus 1, or 1 minus 2 sine squared u. And it really doesn't matter. You'll see here when we get into the examples, it's really going to depend on what you're given to know which one you're going to have to use. If I'm given in something where other pieces are just in terms of cosines, then I'm probably going to want to take this route. If I'm given just sines, I'm probably going to want to go this route. If it truly doesn't matter, then I'll probably take this route here. So example 1 says to solve the cosine of 2x plus the cosine of x equals 0. Well, right now we can't just solve for x because we can't, it's not really simplified. So the first thing I notice is we have a double angle right here, and it's because of this 2x. So I can rewrite that using the formulas that were given. And if you refer to the list that I gave you before or the sheet that I've handed out in class, you'll notice that we have 3 different equations. And really, when I look at those 3 different equations, I see right here I have a cosine x. So whatever I change this to, I'm also going to be adding a cosine x. Well, from solving back in the sections that are early on in Chapter 5, we know that we want to try to keep everything in terms of cosine when we're solving, because the more trig functions we add, the more complex the system becomes. So I'm going to choose the equation, or I'm going to choose to rewrite this right here using the equation that involves just cosine. So I'm going to rewrite this piece right here as 2 cosine squared x minus 1, and then I'm going to add my cosine x, which is what I have right here. And I really have a quadratic equation, so if I write this in standard form, I then have 2 cosine squared x plus cosine x minus 1 equals 0. And if I factor this, I have 2 cosine x minus 1 times cosine x plus 1 equals 0. And now I can set each factor equal to 0 because of the zero product property. So I have 2 cosine x minus 1 equals 0, and I have cosine x plus 1 equals 0. So now to solve, I'm going to add 1, divide by 2, so I have cosine x equals 1/2. Cosine x is going to equal 1/2. Let's draw a unit circle over here. So I'm going to get a value of 1/2. That occurs at increments of pi's over 3's. So I get a positive 1/2 in the first quadrant and a positive 1/2 in the fourth quadrant, which is 5 pi over 3. I wasn't given any restricted domains, so I do need to include 2 pi n with everything. So I have x equals pi divided by 3 plus 2 pi n, and I have x equals 5 pi over 3 plus 2 pi n. So I'll accept either one of those. And then here I have cosine x equals -1. Well, that's only going to occur at one spot, and that one spot is right here at pi. So I know that x is equal to pi, and I have to account for all values since I was not given that restricted domain. So I'm going to add 2 pi n, and I have 3 solutions then between these here and this here. Example 2 wants us to use a double angle formula to rewrite g of x equals 3 minus 6 times sine squared of x. Then we're going to sketch the graph over the interval from 0 to 2 pi. So, using the 3 minus 6 sine squared x, the first thing I've noticed is I can factor a 3 out of both. So if I factor a 3 out, we're left with 1 minus 2 sine squared x. And 1 minus 2 sine squared x, if you look at your double angle formulas, is really a cosine value. So I have 3 times the cosine of 2x. And I'm done. So now if I go to graph this, let's just kind of do a rough sketch here. We're going from 0 to 2 pi. So that's 2 pi, this is pi. This here is pi over 2, and, oops, this here would be 3 pi over 2. And from our equation, we see that this 3 here is going to give us our amplitude. So I know we're going back and forth between a positive 3 and a negative 3. To find your x-intercepts, you can set that equal to 0. So you know 0 equals 3 cosine of 2x, or 0 equals the cosine of 2x. Well, I know cosine equals 0 at pi over 2, so we'll say 2x equals pi over 2, and 2x equals 3 pi over 2. So when we divide both sides by 2, we end up with pi over 4 and 3 pi over 4. So my zeros then are going to be here, 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 and here. And we end up with a curve then that looks like this. And now we're done with the whole problem. For example 3, we're going to use that the sine of u is equal to 3/5. And based upon that, we want to find, and we're looking at the range from the domain from 0 to pi over 2. And we want to find the sine of 2u, cosine of 2u, and the tangent of 2u. Now, if we sketch this, we know that we're in the first quadrant because we have a positive 3/5. And we are given this domain right here. So we're going from 0 to pi over 2. And if I go ahead and I draw in my angle here, so we can call this u, we know that sine is equal to the opposite. So it's going to be this height right here. We know that this is 3 and our hypotenuse is 5. So that tells me then that this coordinate point here is 3, and this x distance then is 4 just by using your Pythagorean theorem. So if I want to go ahead and find the sine of 2u, this is going to give me 2 times the sine of u times the cosine of u. So this is going to give me 2 times, we know that sine u was 3/5. Cosine u is going to be the adjacent side, or 4 divided by the hypotenuse, which is 5. And if we multiply all of that together, we end up with 24/25. And we do the same thing for cosine of 2u. And it really doesn't matter which equation you use. I'm just going to use 2 cosine squared u minus 1. Okay, but you can pick any one that you want. So when I go to plug in for this, I have 2 times cosine we said was 4/5. We are going to square that, and then we're going to subtract 1. So this gives me 4 squared is 16 times 2 is 32/25 minus 25/25, or 1. And this will give me 7/25 for the cosine of 2u. And last but not least, we have tangent of 2u. Tangent of 2u gives us the sine of 2u divided by the cosine of 2u. Now this wasn't exactly given to you as one of the properties, but it's the same concept. And I would use this concept because we've already solved for the sines and cosines. So what that gives us then is sine of 2u was up here, so we have 24/25 divided by cosine of 2u, which was 7/25. So this then is going to give us 24/7 because our 25ths are going to cancel. So this is tangent. Or you could use the property that was given to you on the double angle formulas or sheet and use that formula and you'd get the same thing. Okay, and before we go on, I did forget to add the slide, but we can also use double angle formulas with other double combos. And what I mean by double combos is instead of just 2 theta, we could have 4 theta, 6 theta, 8 theta, etc. These are all doubles. Okay, and just like a little mini example, if I had the sine of 4 theta, I could actually, instead of going 2 sine u cosine u, I'm going to divide that u in half. So in this case, I would end up with 2 times the sine of 2 theta, times the cosine of 2 theta. Or if you were given something like the cosine of 6 theta, this is really the same thing as saying cosine squared of 3 theta minus sine squared of 3 theta. So essentially what you're doing is you are having this right here when you plug it in here. Just like you would if you had the sine 2 theta, then this would just be a theta. So if you have questions on that, let me know. Example 4 says to derive a triple angle formula for the cosine of 3x. So when we're given the cosine of 3x, we can really rewrite that as the cosine of 2x plus x. Now when we do that, we can use the sum properties that we learned back in section 5.4, and we know that this gives us the cosine of 2x times the cosine of x plus, minus, because this is a plus. So we'll go minus the sine of 2x times the sine of x. Now you have a double angle here and a double angle here we need to simplify. So the cosine of 2x is going to be 2 cosine squared x minus 1 times cosine x. And the only reason I chose that formula is because of this cosine here. Then we have minus. Now for this sine 2x, we have 2 sine x cosine x times sine x. So now if we simplify, we have 2 cosine squared times a cosine squared, which is going to give us 2 cosine cubed x minus cosine x minus, then I'm going to distribute this onto here, and we end up with 2 sine squared x times cosine of x. And I can't fully simplify this yet because I have this sine piece. So I'm going to convert that to terms of cosine. So 2 cosine cubed x minus cosine x minus 2 times 1 minus cosine squared x times cosine x. And now if I distribute, this is going to give us 2 cosine cubed x minus cosine x minus. Now I'm going to be actually distributing this 2 and the cosine at the same time. So this is going to give us 2 cosine x, and I have minus in here, and I'm multiplying by this negative 2 right here. So I really have plus 2 cosine cubed x, and that's because of this and this. So now what I see is this right here and this right here, these are like terms. So this gives us 2 plus 2 is 4 cosine cubed x minus 1 cosine x minus 2 cosine x is minus 3 cosine x. And we have just eliminated our triple angle and got it down in terms of single x's. The next set of formulas that we will be given are called half angle formulas. And a half angle is just that, where the angle is being divided by half. And you can read through these. You'll see that you're going to have plus or minus the square root of 1 minus cosine divided by 2. Cosine is going to give you 1 plus cosine divided by 2. And tangent is going to give you either 1 minus cosine divided by sine or sine divided by 1 plus cosine. Now, for sine and cosine, they give you plus or minus. The plus or minus is going to depend on the quadrant in which the angle lies. So we are going to have to pay attention to which quadrant we're in. So example 5 says, find the exact values of the cosine of 105 degrees. Well, cosine of 105 degrees, this doesn't really help us out a whole lot because we don't have exact values for that. But if you keep in mind that one of our values we do have an exact value for is 210 degrees, 105 degrees is half of 210 degrees. So this tells me I can use a half angle formula. So the cosine of 105 degrees is equal to the cosine of 210 degrees divided by 2. So my u is really going to be the 210 when you're using that formula. So this, as far as the plus or minus goes, my original problem said 105 degrees. Well, 105 degrees occurs in the second quadrant, which tells me then that my cosine value is going to be negative, and we'll address that here in a second. So for now, I'm going to take the square root of 1 minus the cosine of 210. I apologize, that should be 1 plus the cosine of 210 divided by 2. So now when I go to simplify, I have 1 plus the cosine of 210 is actually going to give me a negative square root of 3 divided by 2. I'm going to divide all of that by 2, and this square root does go over everything. So now when I simplify my numerator, I have the square root of 2 divided by 2 minus the square root of 3 over 2 divided by 2. So when I multiply by the reciprocal, we end up with the square root of 2 minus the square root of 3 over 4. And when I go and I square root the numerator and square root the denominator, we end up with the square root of 2 minus the square root of 3 divided by square root of 4, which is really 2. So now my radical is no longer over the denominator, it's just over the numerator. And because my original 105 degrees is in that second quadrant, I know that the whole thing is negative. So my final answer then is going to be this right here. Example 6 says to find all solutions of cosine squared x equals sine squared of x over 2 on the interval from 0 to 2 pi. So, to start out with, I'm just going to simplify this sine squared of x divided by 2 for now. And this is really sine of x divided by 2. Let's see, let's write this above. It really looks like this. So I can apply my half angle formula, and the half angle formula for sine is going to be plus or minus the square root of 1 minus cosine x divided by 2, and then we're going to square that. So squaring a square root gives us 1 minus cosine x divided by 2 equals cosine squared x still. And if I want to clear my fractions out, now I have 2 cosine squared x equals 1 minus cosine x. And if I want to simplify this, I have a quadratic formula. Everything needs to be on one side. So I have 2 cosine squared x plus cosine x minus 1 equals 0. And I can factor this, into 2 cosine x minus 1 times cosine x plus 1 equals 0. So now I have 2 cosine x minus 1 equals 0, which means cosine x equals 1/2. I'm on the interval from 0 to 2 pi, so x then is going to equal pi over 3 and 5 pi over 3. So here's one solution set. Then I have cosine x equals a -1. Well, this just occurs when x equals pi. So these are my 3 solutions. Next, we have a list of product to sum formulas. And what this is just different combinations of products. You have sine u times sine v equals this. Cosine u times cosine v equals this. Sine u times cosine v equals this. And cosine u times sine u, or sine v equals all this. Kind of like the sum properties that we had in section 5.4. Again, all of these formulas will be given to you. You just have to know how to use them. So, example 7 says to rewrite the product of sine 5 theta cosine 3 theta as a sum or difference. So, in order to do this, we're going to use this formula. And now we're just going to plug in what we have. So, we have 1/2 times the sine of 5 theta plus 3 theta plus the sine of 5 theta minus 3 theta. So this then is going to give us 1/2 times the sine of 8 theta plus the sine of 2 theta. And that's it. And the last set of formulas that we're going to be given are called sum to product formulas. And these look like sine u plus sine v, sine u minus sine v, cosine u plus cosine v, cosine u minus cosine v. And you can see that these are what you're given. Again, these will be on your sheet. So in order to see how to use these, we're going to find the exact value of the sine of 195 plus the sine of 105 degrees. So to do that, we're going to use our sine u plus sine v. And when I do that, we get, so we'll say equals the sine, we have 2 times the sine of 195 plus 105 divided by 2 times the cosine of 195 minus 105 degrees divided by 2. So when we simplify this, we have 2 times the sine of 150 degrees times the cosine of 45 degrees. Now we're going to have to pull out our trig skills, and we're going to say that the sine of 150 degrees is really 1/2, and the cosine of 45 is really the square root of 2 over 2. So when we multiply these together, our 2 and half are going to cancel, and we're going to be left with the square root of 2 over 2. And that's our exact value. Example 9 says to solve the sine of 4x minus the sine of 2x equals 0. Again, we're going to use our sum to product formulas. And this is going to give us 2 times the cosine of 4x plus 2x divided by 2 times the sine of 4x minus 2x divided by 2, and this equals 0. So now we have 2 times the cosine of 6x divided by 2, which is 3x, times the sine of 4 minus 2 is 2 divided by 2 is just x, and this equals 0. Well, I have two factors. I essentially have this here and this here. So if I go 2 cosine of 3x equals 0 and the sine of x equals 0, I can solve. So this here gives me the cosine of 3x equals 0. Well, cosine of 0 equals, or cosine of x equals 0 when we're looking at pi over 2. So that's going to equal 3x. Or 3 pi over 2, which is also equal to 3x. So when we divide by 3, we have x equals pi over 6. Or x equals 3 pi over 6, which is just pi over 2. So these right here are two of my solutions. And then sine x equals 0 when x equals either 0 or pi. And now I'm done. In the last example for chapter 5, says to verify that the sine of 6x plus the sine of 4x divided by the cosine of 6x plus the cosine of 4x equals the tangent of 5x. So, because we're using sums of sines and cosines, then we're going to have to use the sum to product formula. So to do this, we have 2 times the sine of 6x plus 4x divided by 2 times the cosine of 6x minus 4x divided by 2. And that's all going to be divided by 2 times the cosine of 6x plus 4x divided by 2 times the cosine of 6x minus 4x divided by 2. And what you'll notice then is we can simplify this down to 2 times the sine of 10x divided by 2, which is 5x, times the cosine of x. And we're going to divide this by 2 times the cosine of 5x divided by cosine x. And our cosine x values are going to cancel, and we are then going to be left with 2 times the sine of 5x divided by 2 cosine of 5x. And sine divided by cosine, since our 2's are going to cancel, sine divided by cosine then gives me the tangent of 5x. Now look how much fun that was. And now I want you to take a deep breath as I wish to congratulate you, as you are now officially done with Chapter 5. You've survived. This is the chapter that everyone was afraid of, but you are now done. So congratulations, you've made it through, and hopefully the rest of the year goes well for you, and I will see you guys in class tomorrow. Have a good night.